Firstly, I'd like to thank the organizers for inviting me, and secondly, I have to apologize. I was not aware that English was one of the official languages, so all my slides are in Croatian, but I will try to speak in English, and let's hope for the best. So what I will try to briefly show you are the main seismological properties of the first 6 months of the Petrinja earthquake sequence. That will be a completely seismological lecture. But I nevertheless hope that you will find it interesting, because this is your main enemy. And we seismologists are spies in the enemy ranks. So we will, I hopefully. So let's begin. So this is just an overview of the sequence. The main event occurred on 29th of December. It was magnitude 6.4. The strongest foreshock was just a day earlier, magnitude 4.9, and the strongest aftershock just after the New Year, magnitude 4.8. The maximum intensity was 8 or maybe 8 to 9 on the European macroseismic scale, and it occurred on a strike-slip Petrinja fault. 7 people died, more than 50,000 buildings were damaged. The total damage amounted to over 5 billion euros. Quite often we observed liquefaction, mud volcanoes, and so on. And over 110 core collapse sinkholes occurred in the area. So this may be even larger now. This is about a year ago. So, this is what we are facing. So this is a seismogram of the 1 hour of recording on the 6th of January. So at least 6 earthquakes are seen here. That is approximately 1 every minute. The historical seismicity of this region of the Kupa Valley Petrinja is shown here since the middle of the 18th century. The most important earthquake, is this one here. This is the event, which is one of the most famous and important earthquakes ever in the world, because it enabled Andrija Mohorovicic to perform analysis revealing the existence of the Moho discontinuity. And it was the largest earthquake that we knew in this region until 2020. The strongest earthquakes, as you see, were in 1861, 1909, this one, and its aftershock in 1910 until 2020. The seismogenic source was a little bit of surprise. In the European map of active faults in the shared database, it was mapped as a Petrinja fault zone, which was a transpression source dipping to the northeast, which seems, when you look at the figure, seems rather reasonable. But when you take a more detailed look, you will see that the main Petrinja earthquake was a strike slip, and this one was probably dip slip or transpression with a large dip slip component. Now, we cannot be sure about this one. We did as thorough analysis of the 1909 earthquake as possible, but you should know that seismology and especially seismometry were in its infancy, and the quality of seismograms and the amount of seismograms available was quite low. Anyhow, now we are faced with a strike slip event, which was certainly strike slip. It is revealed by the INSAR analysis, the satellite images, and there's no doubt about it. The problem is, what exactly can we expect in future? Now, this is quite important for what we have been able to record. This map shows the situation with the Croatian seismic network before and when the earthquakes occurred. So the earthquakes are here, and the network is rather sparse. The closest station is about 35 kilometers away, which is quite far. And you should also remember when did it occur. It occurred in 2020, the year of COVID, of all possible restrictions in travel, in everything. And it occurred just, 9 months after the Zagreb earthquake, which really put our instrumental capabilities to test. And we have spent almost all spare seismographs that we have enhancing the earthquake, the network around Zagreb. So we really had a terrible year. That this is an experience I'm not sure anybody ever had. 2 disastrous earthquakes during pandemics. Anyhow, the Italian colleagues from the OGS Udine offered to install a temporary small network, which is the yellow one, rather soon after the earthquake, as soon as we could do it, because they needed to get COVID permits to come in Croatia, organize everything. But we started deploying on 4th of January and finished on 5th of January. This is the yellow stations around here, close to the earthquakes. And on 15th of January, the seismological survey started installing the brand new 30 stations, which were rapidly acquired thanks to the donation of the government. As the result, those are the red ones. As the result, we have the by far best recorded earthquake sequence in the history of Croatia and the neighborhood. Why is it important? Why did I spend so much time on the network? Because of these 2 figures. So this is the mean 1 confidence radius reflecting the aleatory uncertainty, so the uncertainty embedded into the data. From the day 1 until the deployment of the first network, the yellow one, the depth was on the average plus or minus 3 kilometers or even less. As soon as those 6 new stations were installed, this dropped down quite dramatically. This was unexpected even to us. We had no idea that the impact will be that large, and it was even larger on the epistemic variability. I will not go much into detail, but you can appreciate the huge difference that it made. And when the deployment of the 30 new stations started, this uncertainty fell down even more. So we have a drastic reduction of the uncertainty after the additional networks were installed. This is the temporal decay of the number of earthquakes for, I think, magnitudes probably larger than 2. And you see the theoretical Omori law in black. So if this persists, then we will have our background seismicity to the level before the earthquake in 2020 in another 10 or 12 years. Now about locations. This is just for the first 6 months of the sequence, so until 28 June 2021. We were able to locate almost 14,000 of earthquakes. To do that, we had to, not we, but my co-author sitting there, to read from the seismogram over 250,000 phases on all seismograms that were available. And the result is on the right-hand side of the slide. So it shows all located events. And you can see the main epicenter clouds well, nicely aligned along the Petrinja fault. But you can also see additional groups of epicenters off the main cloud. Some of them even rather far away. We will see possible reasons for that later. Now, if we only look at the most reliably located events, you can plot them over the INSAR image, which is unwrapped phase. So you can see the largest amount of horizontal movements in these two patches, one towards east, the other towards north, and most of the earthquakes really occur within those patches, with the exception of these, which are apparently somewhat outside the main displacement area. An important part of all seismological analysis are the focal mechanisms. Just briefly, so analyzing the spatial distribution of first onsets on seismograms, we mostly can determine the type of focal mechanism, so the type of fault that caused the earthquake and the geometry of the movement along the fault plane. The Croatian database of fault plane solutions now has about 400 events dating from the 1909 event. And in this series alone, we were able to compute 75, which is an order or more than an order of magnitude more than for any other earthquake sequence, of course, thanks to the large amount of data that were available. Those are beach balls diagrams. So the beach balls with red compressional quadrants and which are crossed like that are strike slip events. So the events where fault wings moved horizontally one past the other. And the blue ones are the reverse fault events. And you can see that although the main shock and most of the largest aftershocks were also strike slip, there is a large amount of dip slip earthquakes that were occurred as aftershocks. And in fact, 50% of them were strike slip and 50% were dip slip. So this is also a thing that we did not understand at first. Maybe we still don't, but we'll see something about it later. On this figure, you see the strike of the inferred p-axis. This is sigma 1. P-axis of the tectonic stress field. And when you compare this one for the main shock, which should be more or less parallel to the regional stress field, you will notice that aftershocks mostly have clockwise rotated p-axis by about 16 degrees. Now we can do some vertical cross-sections. The first one is a longitudinal one along the main cloud. And this is the cross-section. It is superimposed on the coseismic displacement model. After Castellitz et al., the author of the model is Simone Azzori, which shows that the main bulk of energy released by the main shock was at a rather shallow depth. This is the hypocenter. So the model is that the rupture proceeded from here towards the surface and to the northwest and southeast. with the bulk of energy being released at about 4 kilometers in a rather small patch here. And the aftershocks that you see here are mostly below the area of the largest displacement, because the main shock, together with the foreshock and the largest aftershocks, released all stress here, so there was nothing to break anymore. Those are some other cross profiles across the fault strike. And you can see that in space we have a rather good grouping of hypocenters, which seem to reveal that not a single fault was active, but a group of faults, of most of which we had no idea that existed. So, the results so far raise some questions. The first one is, how can we explain the rather unusual distribution of hypocenters of the aftershocks with the depths exceeding 15 kilometers? This is surprising because the heat flow in the area is rather high, about 65 milliwatts per square meter, with the high geothermal gradient of about 45 degrees Celsius per kilometer, which translates to the temperatures of over 800 degrees at, say, 18 kilometers depth. And this is much larger than the temperature where standard granitic crustal rocks are expected to become plastic. This is well over the ductile brittle transition in such rocks. So we should not see practically any activity below about 9 kilometers. Evidently we do. So for now we have no other explanation but to hypothesize that the hypocentral area is probably made of rocks of the oceanic origin, of ophiolites, and we believe this is reasonable because the ophiolites are found very, very close, even in very close vicinity of the area, on the west of the Sava-Vardar suture zone, and the ophiolites become plastic only at about 720 degrees Celsius. So we think that it is reasonable that this part of our country is dominated by ophiolites at these depths. Furthermore, you remember the odd distribution of epicenters all around the main cloud, and you remember that 50% of aftershocks were strike slip and the rest of them were dip slip, with the p-axis rotated by about 15-16 degrees clockwise. So this can be, perhaps, we hope, explained by the Coulomb stress failure hypothesis, and this is well-established theory. Now I will not go much into details. We have seen this equation in the previous lecture. I will only say that we've used Coulomb 3.3, which is, well, state-of-the-art program that is used. And mostly we use it to model the change in stress induced by the occurrence of the earthquakes. So the earthquake occurs because the stress is increased. Now when it is released, this disturbs the stress around in a rather wide area around the source. And Coulomb 3 is used to identify those areas or those faults where the change caused by the earthquake will either increase in red or reduce the probability of faulting. And you can do it for known faults, or you can do it for the optimally oriented faults. assuming they exist. So we did that. So this is the model of the source of this source. You can see it in 3D here. The maximum slip in this patch was modeled in 3.5 meters. This was, by the way, a very high-stress earthquake, which indicates that the fault may be not so mature. This source theoretically describes what we have observed in INSAR. You see the arrows here, and they correspond to these. This is the vertical theoretical displacement, but more interestingly, you can see in yellow and red, you cannot see blue, but there is faint blue here and here. You can see this rather typical pattern for strike slip faults with 4 lattices. So if we have optimally oriented faults in these red-yellow areas, then those faults were brought closer to rupture than before the earthquake. So we may expect the aftershocks to occur only in these areas. And you can see the aftershocks here, perhaps they're in black. And all aftershocks indeed occurred where the computed Coulomb stress change was increased on the optimally oriented faults. So these are all optimally oriented faults for all depths, but we can see whether the theory or the result holds for separate groups. And this is the same thing for the reverse faults. Again, all the earthquakes except this one are related to the areas of increased stress, and the same for the strike slip events when all except this one are within the expected areas. So now we know why, even those very far away, you know. So now we have a reasonable explanation of why the earthquakes occur where they did, but this requires that these faults have existed there. So it may be that the tectonic activity in this area, the tectonic history, is much richer than we have evidence in the seismicity that we know so far. And we have a lot to do. We have to do detailed modeling of the temporal evolution of the rupture. We will need to identify the missed small earthquakes because they were hidden in the codas of large earthquakes, in the noise and so on. There are advanced artificial intelligence computer techniques to do that. We will have to locate all earthquakes with all possible nonlinear 3D models, algorithms which take care of relative locations and so on. Using all that, we will have to map active faults. This is a very, very, very preliminary version of my ad hoc try. We hope that the large set of quality data will enable further analysis of wave attenuation, anisotropy, tomographic research of the upper crust, and many, many other things, exciting things. It will also contribute to the new seismicity model of the wider Petrinja area, and we wonder whether it will really change the hazard assessment here. My guess is no. But nevertheless, let's see, because it's at first confusing that Zagreb is here and Petrinja is here, and the Petrinja earthquake was 6.4 and Zagreb earthquake was 5.5. So why is the hazard here so much lower? I have the answer, but it probably is not. Let's keep it for now, maybe in questions. So the conclusions. We have the first opportunity to make a detailed analysis of the devastating strike-slip earthquake within the tectonic plate. So this was intraplate earthquake. Those are rare in the transition zone between the Dinarids and the Pannonian Basin. We have rather precise, reasonably precise locations of the earthquake foci, and together with focal mechanisms, we have by far, so far, the best insight into the structure of the Petrinja earthquake system. The Coulomb stress change excellently explains the distribution of aftershock epicenters. It seems that the earthquake activated two groups of faults, reverse and strike slip. There is a strong indication that the crust is dominated by ophiolitic rocks. And of course, we hope that this is not the end. As I told you, we really have a lot of material for the next generation. And that's it. Thank you for the interest. It has just been done, and it will be published soon. I was not directly involved, but it seems that the kinematic model is very simple, with not many stops along the fault. It was a rather slow rupture, but with a very large stress drop.
And then a quick question. I was very curious to understand how the global tectonics matches with what was happening, given that this is an intraplate earthquake. Do you have any geodetic station in Croatia?
Yes, there have been several, even in the neighborhood. But this is not, this is the earthquake that we should have expected, because it is intraplate, but it is between the very large, almost independent units of the European plate. So you see the driving forces from the Adriatic plate, which collides with the Dinarids, and the Dinarids, this is just in the transition zone between the Dinarids and the Pannonian Basin. So this is a very known large fault system that goes from Slovenia down to Montenegro. Banja Luka is practically on the same system, and this is not, we know the mechanics, why it occurred, but we were not sure that, we were not aware that the strike slip fault will be, because it is still rotated, that preferred faulting we thought would be transpressional, but it seems that it is practically vertical, and then it makes sense.